All right, good morning, everyone. I believe I can just go ahead and start. I'm sure Romy will let me know if this isn't working correctly. Again, my name is Barry Stoddard. I'm at the Fred Hutchinson Cancer Center, and I'm going to be presenting a series of slides just summarizing some structural work that led to the computational challenge at D3R, conducted as a collaboration between David Baker's lab at the University of Washington and my own lab at Fred Hutch. Unlike most of the challenge work that's been going on at D3R, this is kind of an orthogonal project to that of drug and inhibitor design, in that the structures that we provided are of computationally designed, and then laboratory evolved ligand binding proteins intended to be specific and high affinity for defined small molecular ligands, rather than the inverse designed small molecules intended to bind a defined protein target. We provided two sets of iterative structures of designed ligand binding proteins late last year. One set of designs and evolved proteins intended to bind 17-hydroxyprogesterone, and then a second set of structures of designed proteins intended to bind 25-hydroxyvitamin D3. So I'll just walk through these structures and give you just a summary of the crystallographic analysis and some important points. And I'll start with the crystal structures of design binders for 17-hydroxyprogesterone, the chemical structure of which is shown in the lower left corner of this slide. This is a relatively rigid steroidal compound with 3 potential hydrogen bond donors or partners spread across the molecular structure. These all stem from an original PDB structure 2A15 and were subjected to an original round of computational design to create the first ligand binder, which we call OHP9, and then subsequent site-directed mutagenesis and selection experiments that generated a pair of refined higher affinity ligand binding proteins, one of which had its structure solved and is called OHP91C. The binding affinity established for these proteins for the original computational design, a rough estimation, but somewhere sort of low micromolar affinity, and then for the evolved variant, not surprisingly, a higher affinity, now sort of mid-nanomolar KDs determined by fluorescence anisotropy much more accurately. So 2 crystal structures were provided by our group to D3R, the first of OHP9 and the second of OHP91C. The most important points to note here is the resolution of these structures, 2 and 2.5 angstrom resolution respectively, and the fact that for both structures we were able to visualize multiple independent views of the protein ligand complex, which becomes very important, as you'll see in the next 3 or 4 slides. 4 independent views of the complex to OHP9 and 6 independent views of the complex corresponding to OHP91C, the directed, laboratory evolved variant. So OHP9, shown on the upper left, is the original computational design with the ligand in its computationally designed pocket. Shown on the right is the corresponding crystal structure, an overall fold of the designed protein, and then an overlay of the model and the crystallographically refined structure. What you'll see is that the unbiased 2FO-FC difference map is well resolved and very clearly shows the ligand bound in the intended pocket in the protein. However, close examination of the design versus the crystal structure shows that while the ligand is bound in the design pocket, it's bound in a mode and an orientation which is rotated about the long axis of the ligand by 180 degrees, basically flipping the molecule entirely over end on end in that design binding pocket. Shown here is our the 4 independent views of this bound ligand in the crystal structure, and the most important point here is something really kind of unprecedented. I've not seen this happen before, but potentially very interesting and useful for computational work, which is that we see 4 views of the bound ligand in the pocket, 3 of which show the ligand in very similar bound conformations to one another. Chain B and D in particular are virtually identical. Chain A has a slightly different pucker of this ring system right here. But in the fourth copy in the asymmetric unit, what we see is that there's an additional rotation of the entire bound ligand now around the long axis of the molecule, basically putting it into the same pocket and still with hydrogen bond donors and acceptors located at each end of the molecule, but clearly a different bound orientation. And again, this is at relatively high resolution. This is very easy to see. This is very unusual to see for a protein ligand complex. Normally what you would expect to see if there's this sort of conformational heterogeneity in a binding pocket is you just expect to see average density over the dynamic distribution of the bound complex. And what this indicates is that clearly while there's more than one possible binding mode for this molecule, there's enough of an energy barrier separating these bound positions to allow them to have a substantial residency time for each individual form of the bound complex. And as a result, the crystal lattice was able to basically pull these individual complexes out of solution and deposit them uniquely and individually into specific individual positions in the 4 copies of the complex in the asymmetric unit. So this structure basically ended up providing more than one bound orientation and position for the ligand within this design binding pocket. So in contrast, and this is just a map of the contacts to the hydrogen bond, potential hydrogen bond partners as originally designed by Rosetta Design, targeting these 3 positions around the molecule, and the contacts that are observed at a distance of 4 angstrom or closer to the 4 individual chains in the structure. And again, the one that differs by rotation around the long axis of the ligand is chain C, as shown here. Regardless of which conformer you look at, the same relative side chains are capable of making satisfactory hydrogen bond contacts to the individual potential partners around the molecule, as shown here. What's not shown in this, of course, are all the surrounding side chains that basically build up the remainder of the binding pocket and establish surface complementarity to the molecule. So the story is different with the evolved variant, which now displays an affinity that's low to mid nanomolar Kd. So again, the bound ligand is located within the intended binding pocket. Again, as in the original OHP9 computational design, the molecule is rotated by 180 degrees about the short axis orthogonal to the plane of the molecule, similar to chains A, B, and D in OHP9. But in this case, the molecule is clearly settled down into one relatively uniform bound orientation and position in the binding pocket. We have 6 independent views of the molecule, again at relatively high resolution, 2.5 angstrom resolution in this case, in the asymmetric unit. And as far as we can tell, all of these molecules are... I'm getting some conversation coming over my headphones, sorry. All 6 copies are found in more or less the same orientation and binding mode within the binding pocket. They're very closely related to one another. So this to me would appear to indicate that as a result of mutagenesis and selection for higher binding affinity, that one particular binding mode has been selected at the expense of the others relative to the original computational design. And things are a little bit more locked in place physically. So shown here again is just a map of designed and observed contacts to the individual potential hydrogen bond partners around the ligand for Rosetta Design and for the crystal structure. Again, with anything 4 angstroms or closer denoted by the dashed lines. Again, the various hydrogen bond donors and acceptor partners are relatively satisfied in this pocket. What was not obviously computed in the original design but is observed in this crystal structure are the presence of hydrating waters that are participating in the coordination of the ligand. So moving on to the second series of 3 structures that we provided. So this is a different computational experiment for ligand binding design. This was an unusual project in that the original computational design was originally for design of binders against THC. That project as a whole was relatively successful, but during the course of examining the binding specificity of various designs, we found one particular design called 4424, which was observed to actually have measurable significant binding for vitamin D3 rather than the intended ligand THC. And so that particular initial computational construct was then pursued through a series of additional mutagenesis and selection to pull out a little bit higher binding affinity, initial rounds of computational docking specifically to try to improve on affinity for vitamin D3, and then multiple rounds of mutagenesis and selection to try to affinity mature the molecule, leading to a series of 3 crystal structures relative to all these constructs shown on this flowchart. And again, the ligand vitamin D3 is shown here. This is a little bit more flexible molecule with only 2 potential hydrogen bond partners located at the very distal ends of the ligand. So this project really relies a great deal on steric complementarity to try to build up an appropriate binding pocket for this ligand. With regards to the crystallography, the important points is that these are very high resolution structures. They're all 2 angstroms or better. We have fewer independent views of the protein ligand complex in each structure. Moving on. The original model produced by Rosetta places the ligand in this binding pocket as shown right here, and the crystallographic analysis again shows that the bound ligand very clearly is bound in the intended pocket and is well resolved in electron density and unbiased 2FO-FC electron density. Again, superimposing the design versus the crystal structure shows that there is a rotation, and a 180-degree inversion of the binding mode of the ligand relative to the original design. In this case, it's not an end-over-end barrel roll. It's a more simple rotation about the short axis of, relative to the length of the ligand. So just a simple roll within the extended binding pocket. Shown here is just the quality of the electron density that supports that structural modeling and refinement. 2 independent views of the bound ligand in the design pocket of the computational model. Again, just a quick map of contacts to the potential hydrogen bond donor and acceptor partners of this ligand, one of which points out towards the exterior of the binding pocket, the other is completely buried. There's both there's a designed contact to a glutamic acid in the bottom of the pocket, and we see that contact is preserved, although the directionality of that hydrogen bond contact is different than in the original design. In the evolved variants, the binding mode of the ligand is preserved. It does not change. It's basically the same result as we've seen before in the previous crystal structure. Only 1 independent view of the ligand bound in the pocket, again, is shown here in the electron density. And again, the role of this glutamic acids at the bottom of the binding pocket is preserved in this complex, and there are some additional contacts mediated by water that sort of fill in the hydration sphere around this oxygen on the ligand. And the final evolved variant, the story is pretty much exactly the same. Very, very similar binding mode for this molecule, and really an unchanged series of contacts to the hydrogen bond donor and acceptor. So that's an overview of the crystallographic analysis, as well as a summary of the origins of this project, which once again, just to reiterate for anybody who popped in late in this is a protein design project building protein scaffolds intended to bind defined ligands rather than a inhibitor or drug design project targeting a static binding site. And thanks very much for everybody's attention, and I look forward to hearing details of the computational work that was performed.